Hello everyone. Yeah, it's a couple of really good presentations obviously already on day one regarding when and where to separate, regarding earthing, regarding risk, and it's always nice to present later in the conference because you get to reflect back on some of the things that others have said. Let me go here. Safearth, real quick, who we are. We're a pretty large electrical engineering firm now. We're up to 70 worldwide with our American and UK contingent. We've contributed to a lot of Australian standards and international standards. The IEEE suite of standards are all about to be re-released, hopefully this year, with a lot of changes. And IEEE, even though we don't necessarily follow those standards as much anymore, we tend to be following European standards that impact our AS2, AS67 and so on, but IEEE has a big impact worldwide, especially with standard 80 and 81. So you could see those come out soon. I couldn't believe it when I looked up, the Kudal incident that we helped, well, I actually investigated personally with my mate, Matthew Bale. That was 10 years ago, and I'm sure lots and lots of people in the room know about that incident where the lady fatally received an electric shock in her shower, and it was all very sad and all very avoidable because the fellow who operated the quarry really let it run into disrepair, and he did his own electrical wiring and left an MEN link out, kind of like an old car. I liken it to an old Jaguar or something where you rebuild it and then you find all these parts and the thing still works, right? And that's kind of what happened in that situation. And a motor was running rough and it had a persistent earth fault, and then she just happened to be in the wrong place at the wrong time and she got killed. So that wasn't very pleasant. And that was, 10 years ago. It's amazing how quickly things tick along. Just to introduce the concept of this earthing topic of where to bond or not, I found it very interesting, obviously with the guys working on the old Westcliff winder project, and winders in general. John Weaver knows very well. I've been down in the Metropolitan winder with him, and I'm sure he did it just to scare the hell out of me, and I never want to go into it ever again. But when you think about what you're trying to achieve in either bonding or separating, obviously one of the things that the regulation likes is the idea that you can separate your surface workings from your underground workings in a coal mine. Now, it's desirable because we don't like the idea of gaseous coal mines receiving a lightning strike to the surface workings and that transient entering whatever services, all the way to the bottom of the pit, where it might find a gap and it might create a spark and it might ignite something. And it has happened. It's not like it's, that's pretty remote. It's one of those foreseeable possibilities that we have to try and mitigate as well as we can. It's a very interesting point. Like, it did blow up a coal mine in the US. They believe that was a lightning strike incident that caused that. So we try and do our best to create that separation, but it's incredibly hard. Also in this little talk, I'll go through a little bit of earthing theory purely just to refresh people's memories. I mean, I know a lot of people talk about it as a black art. I've been doing my current job since joining Bill Carman's Energy Australia team for 20 years now. And at times I found it incredibly complicated, difficult, hard, and now I find it incredibly simple. So I'll go through a couple of little things there which might help, especially on some of your fault limited systems, which are really quite easy to design to. And earthing generally, in the principal requirements of why we want to earth things, I'll talk about the three key reasons as well. Really quickly, bonding obviously is introducing a connection between two things, two items, so that we ensure, I've got ensure there in italics because obviously I stole bits of this presentation from a presentation that one of my colleagues must have given, and he made it very clear that it ensures that two things can never be at different potentials. One thing I've learnt through earthing is that a lot of people start to assume that an earth conductor has zero impedance. And that isn't true, because obviously if you've got a long enough connection between two things that you're trying to make equipotential, as soon as you have significant current flow through that, they will be at different voltages. So don't just blindly assume that your equipotential bond makes things exactly at the same potential, because it may not. It eliminates the risk of spark between parts. Again, I wouldn't necessarily say that's entirely true, because it depends on how well the connection is made. You could introduce a spark. Once you bring things too close together, if you put a lug onto a painted surface and you don't prepare it properly, well, then you've probably created all the mechanisms for a spark to initiate with a high enough voltage to break down that insulation of the paint, as an example. So I suppose bonding, it's a simple concept, but you can get things wrong. Separation, on the other hand, is where you intentionally try and make things stay at different potentials. During earth fault, maybe one system will rise to a potential and you want the other thing to absolutely not. A very good example of separation is in HVLV transformers. We use them in the mining environment, but also in the distribution environment around more country areas where you intentionally separate the high voltage earthing system from the low voltage earthing system. You're trying to keep the voltage on the low voltage system as low as it can be more often. Whereas a common earth system in a distribution transformer, any earth fault you have on the primary side will see the neutral and will lift the entire system. So for example, bathhouses on our mine sites, you might choose or want to have a separately earthed HVLV supply supplying that bathhouse. I guarantee you a good designed, a well-designed separately earthed system will produce lower volts on the neutral more often. That's just how they work. I've got another image later, which I really should have put after this one to talk about separation, but when I come to it, I'll remind us of it. It's something you've probably all seen. But here's an underground environment, obviously, where you probably want everything bonded. There wouldn't be a reason under there that you'd want to separate things, unless it was very, very particular and very special. So in this sort of environment, the mesh, the piping, the stand, and commonly our guys will be in these environments trying to guarantee for you, for the mining operators and the owners, that everything is connected together. If you find something that's not, well then obviously you risk assess it perhaps and you decide whether or not you really do want it to be bonded. So that's pretty straightforward, that environment. All right, a little bit of theory real quick, just to give you guys a bit of a helping hand in the right direction. A black art, actually I think it's really quite straightforward. It's really Ohm's law. The earth resistance of a grid is entirely about area. Absolutely area. The resistivity of the soil, sure, we can measure that, or we can guess it, or we can use a previous report and say, well, it's going to be between this and that. It might be 100 ohm meters, it might be 10, it might be 500, who knows, depends on where you are. But if you know the soil resistivity and you know the size of your grid, you can very quickly come up with a calculation that tells you that the earth grid's going to be about 4.4 ohms. It's pretty accurate, 4.4 ohms. I should have probably said 5, but you can really knuckle down onto a number pretty quickly with that simple solid plate equation formula. And so you imagine you've got a bunded transformer sitting there and you've put an earth ring around it and it all measured up to about 10 metres by 10 metres. That's a very, very handy formula. If you need more area, you can go down. And earth electrodes are a pretty obvious thing, but they increase your effective area of your earth grid by going down. And the formula there, these formulas are out of IEEE 80. You'll find them in our ENA EG1 document. That formula there, again, pretty simple, resistivity on 2 pi L multiplied by a little logarithmic formula. In 100 ohm meters, a 10 metre deep electrode will get you 12 ohms. If you put 4 in each of the corners, you'll get down to around 3 to 4 ohms. If you combine this little new system with the previous system, you'll get down to just below 3 ohms. But you can see what's happening here. This MER thing, this mutual earth resistance thing, is where you're starting to oversaturate your area with copper and you just can't get it down any further. So you've got to make some decisions. If you need it to be lower, then you need to probably do something else. So that might be fine. You might have done your job now. If you're on a 10 amp fault limited system, you can design that. Basil, your next job is to design that for Wilpinjong on a back of an envelope, and you'll get pretty close to the answer you want. So that's pretty cool, right? If you want to go even lower, say you're on a 200 amp fault limited system up in the Hunter Valley, or even worse, if you're on Endeavour Energy 66 down around Appin, where it's not fault limited, then you might want to do something else. You might want to start introducing the idea of bonding in the DNSP earthing system, if they'll let you. I'll come back to that. That really irritates me when they don't let you. You know, it's crazy. But an overhead earth wire, earthed well along its route all the way back to its source, will carry about 50% of the fault current back. A really well-designed cable design with good quality sheaths, bonded properly, bonded at each end, will approach 100% of its fault current return. Now, I know that might sound crazy, but I'll give you an example of why that has to be the case. So probably below us, or maybe just over there a little bit, not very far away, is Ausgrid's City Central New substation. It supplies 11 kV to most of this part of Sydney, and there's a couple of other ones on a 132 kV ring. The fault level's 50 kA now on that 132 kV system, and the substation would be, the footprint would be half the size of this room. And so you think to yourself, well, I told you earthing's a bad area. How on earth can we run 50 kA 132 kV system into City Central New substation and make it work and make it safe? Well, the reason is because a 132 kV fault does happen because they accidentally turned the sprinklers on at Daly Street not long ago during a fire test, and they tripped out the 132 kV system, which cascaded, and Sydney tripped out for a little while until they brought it back online again. So there would have been an earth fault, and the cable screens can take about 99.8, 99.9% of the fault current, which means the earth grid and the rest of the distribution system only has to deal with, you know, that point something percent of the 50 kA, which makes it a tolerable situation. So it's pretty amazing. That's mutual coupling. It's no different than how transformers work. You have a primary winding which has current in it. You have a secondary winding which develops voltage due to the EMF association. It's exactly how that works. Same thing. This is probably where it starts to get more complicated. So you can't really do this Basil on the back of your envelope anymore. You probably have to get some more fancy software, go to your consultants. You know, Phil's here. Phil's never got enough work on, so just ring up Phil and get him involved. Where's Phil? There he is. Here's an interesting little photo of a little transformer sitting on an open cut side of a hill. The overhead earth wire, which you can see running over the top, probably isn't connected into the earthing system. It may be, but on face value, you're probably looking at it thinking, well, the designer here decided I'm going to provide lightning protection for the asset and I'm going to keep the system separated because it's got a trailing cable. The trailing cable, in this case, probably doesn't go underground, but it might go across to a piece of equipment, powering it, drag on or whatever it is, or a bucket. In this instance, without the earth wire connected, obviously it won't return fault current in the same way, but it still will. And I'll tell you what else will happen. If that earth wire runs all the way back to its source, and even if it's, let's say it's a 200 amp fault limited system, 200 amps is still pretty reasonable current, that'll produce a voltage on that earth wire, and because it's unearthed at that point, it'll create what I call a coupling factor change or an end of line effect, which will put a really, really big voltage on that earth wire termination at the ground. So you might find that you could design the sub, it might have a 1 ohm grid, you might have a 200 volt EPR, and you might think, well, that's sweet, no problem. But the voltage on the ground near where the poles are earthed could be out of phase with that, and it could be a very high voltage. So you've just got to be a little bit careful about some of these separations that you want to put in place for a particular reason, and make sure the designers, make sure you're aware of what happens when you do that. It can get a bit funky. Back to those three key aspects of earthing, and I really liked when Tim Wiley talked about trying to initiate or making sure you can initiate an earth fault. And that's why we earth things. That's why we earth our equipment. That's why we earth the transformer at the start point, because you want to see that earth fault and you want to detect it and trip it as quickly as you possibly can. So to me, I actually think that's the number one priority for earthing. And then I think the number two priority for earthing is operational, because you want to ground your transformer, you want to ground your power system. You need to keep the voltages within some specified limit so you don't create over voltages on your insulation and break the system. And then third, well, safety, because we all think earthing's about safety, right? And I always say to people, well, if earthing's all about safety, why do we have graded protection schemes? You know, it's all about keeping power on and being able to sectionalise systems. If earthing was all about safety, we'd have absolutely everything tripping instantaneously. We'd have a very unreliable system. We'd always be switching it back on again. But I haven't spoken to this forum for a number of years, but I remember speaking when it was at Piedmont a few years ago, and I kind of made that statement, and a lot of people look at me like I'm an idiot. But one fella, Bob Lee, God love him, his son works with us now at Safearth, he's an instruments engineer, but Bob Lee got up and said, absolutely, that's exactly what I want to do that at my pit. But you've got to be careful, it probably creates all these other flow-on effects that you weren't considering, right? You get a trip down in your mine and then all the power goes out, so you've got to have some system in place to be able to manage that. But like I say, if earthing was all about safety, we'd be tripping things way quicker than we do. The other statement that I like to make too is that earthing things isn't necessarily the silver bullet or the safety panacea, as some people say. So I'll talk a little bit about that now. Transmission line earthing is a complex job because your transmission line earthing really is all about lightning protection for the lines and keeping the equipment working. So we earth the structures to the earth wire so that the lightning transients have a nice low impedance path to ground so that they don't create over voltages, don't stress insulation, and don't create earth faults on our major transmission systems like our 500 and 330 kV systems. If you earth a structure too well, so if you went nuts and this particular structure or pole, maybe it's a pole on that runs through your mine. I know there's lots of contention about some lines going through some mines out near the Ulan area and Moolarben and so on, with all these renewable energy zones that are going in, and you're probably yours as well. If you have, say, for example, a low voltage board on a pole that's near that system, it will very much be impacted by an earth fault on that line. Now, if there's a lot of earthing at that pole, you'll get a lot more current into that structure, and that will create soil voltages that may impact your low voltage board. You can actually control how that works. If you increase the current density by having a smaller earthing system, having a higher impedance earthing system at that one pole, you probably won't change the lightning performance of the line much, but you can absolutely solve the problems at the low voltage board structure. And so I've done quite a lot of transmission line designs, particularly in Victoria, where we've done that especially because they've run new circuits to wind farms and so on, and you follow the route through. LiDAR would be fantastic, and then you identify and you see some farmer's LV connection right near a structure and think, well, what are we going to do here? You could unearth the pole completely, but that creates some issues with insulation. But you can absolutely design the earthing system there so that you don't have to go and touch the low voltage asset, you don't have to do anything different to what the farmer has, and you can really control it very well. The introduction of earthing where it didn't exist prior, obviously, if you didn't have something there before and you create an earthed environment, and suddenly you've got something to deal with. And in Victoria, I don't want to talk about the Victorians too much, they're all a bit weird, but in Victoria, down to Toorak substation, there was a perfectly fine 66 kV open wire connection from Richmond terminal station down to Toorak, and it was completely benign, no problems at all, and they said, oh, we're going to underground it, because all the rich people in Toorak wanted it gone from overhead and they wanted it undergrounded. Well, suddenly they needed to create a cable design. Suddenly the cable design was horrible, and you've got all these hot spots now along that entire route where you never had them if an earth fault was to happen. So it's kind of one of those things that we think, oh, we're just going to earth stuff. Yoo-hoo, great. Doesn't always work out. Obviously, the simple ones, like when we've got stuff outside of our main substations and we think, well, geez, do we earth them? Do we not? What about things that are inside the substations? Do we earth them? I know Endeavour Energy years ago tied themselves in knots. They started building all these beautiful architecturally designed indoor substations. They were 33 kV in cables, 11 kV cables out, and then they had bollards out in the car park, and the project managers were going, oh, bugger, I've got to get this earth from the grid all the way over here under the concrete that's been poured to earth that one bollard. And we said, you know, because it's stated very clearly in their design standards, you have to earth every bit of metal that stands still long enough in a substation. And we helped them understand, with the right sort of risk assessment and words, you don't have to earth everything. You know, if it's too hard, then assess it and risk it and look for an exemption, just like some of the other speakers have been talking about, needing exemptions for certain things. You can absolutely do that. You know, if there's no foreseeable risk of direct or indirect energisation and there's no touch voltage hazard at that thing, then don't earth it. You might make it worse by earthing it. Underground working. So the guys that did the project at Westcliff and obviously John over here with his mess at Metropolitan. Sorry. I mean, they were old assets and old infrastructure. And how do you try and make that separation that the regulator wants you to have of 15 metres in ground when some of these systems were probably fully continuous? So what's the problem then with it being all bonded? What's the problem with having your surface operation connected down into your mine? Does everyone think that you absolutely have to? Who's a show of hands? Who thinks we all should separate the surface works from the underground works? Yeah, there's a few. Who thinks we should just bond everything together? There's a few. Yeah. I would say this, it absolutely makes for a simpler system. It absolutely keeps voltages lower more often, which is great. The only problem is the what if. And you look at that image before of the underground environment with roof bolts and cage mesh and everything else. And if you miss one of those connections, if you have this nasty little latent gap that's not earthed properly, and then you do have a lightning strike hit the surface, which ideally in that bonded environment, it might dissipate nicely and create an overall lower transient voltage rise. But if it finds it way down to that little gap and it sparks, and for some reason the ventilation isn't as good as it was that day and there's a little release of methane and it wants to ignite it, then that's when you're going to be in trouble. And that's that foreseeable problem, just like the White Island problem. You know, it's foreseeable risk, so you should probably try and mitigate it as much as you can. But it's not easy, you know. You've got to really work hard to try and go through that whole list of things you've got to try and separate and maintain that separation. And the last one is this thing that's bothering me at the moment, and I get rather irritated about the DNSPs, and it's this idea of connecting to the network service provider earthing system. Here's a mine up in the Lithgow area, I think, and the overhead earth wires entering that asset are not terminated to the earth grid. You can sort of see them. It's not a great picture. You can sort of see them come around and kind of earth at various points, but not perhaps to the earth grid. Here's one of Endeavour's substations where they absolutely have the earth wires terminated to the landing gantries. So they'll earth their own assets, but sometimes they'll get funny and not earth yours. Or maybe you said to them, well, we don't really want to connect to you. Here's another one of their systems where you can see that the earth wire lands on a disc insulator, and what's coming out and running down the gantry is not the earth wire, it's actually the pilot wires that are inside that old style of steel catenary earth wire. It's called Hardex, and it's got 5 pilots in it, and it's a pretty old system. They don't tend to use it anymore, but it created all sorts of problems. That particular substation's at Kellyville in Sydney, and we injection tested over that feeder, and the substation was fine, no real problems with the sub. Had lots of connections into lots of things and had a really low earth potential rise. But the last structure out across the road had a voltage rise on it of thousands and thousands of volts, all due to induction into the overhead earth wire because it wasn't earthed at the very end of it. So you get this end effect problem where you've created a separation, whether you meant to or not, and the voltage rise on this pole that was in public access that people could just stand at the corner and lean up against had thousands of volts on it during a fault. So it's pretty remarkable how these sort of these issues manifest and create hazards that a lot of people don't realise are there. So let's just have a quick pros and cons of bonding to them, and we'll see if we can work out whether we should or shouldn't. All connected together, it's one system. We don't need to manage the separation. We don't have these nasty voltage rises that can occur. The system impedances are lower. We can utilise current return into the earth wire to keep our voltages lower. It might give us more options in the separations that we want to make on our mine site. It could give us a few more tricks up our sleeve. It improves lighting performance and security at that point as well, and insulation coordination. And it improves the shielding factor as well. Now, this is probably more of a their problem, but if you own the line perhaps across your site, like these guys did in WA, there's a power line on the left-hand side of there, 66. It runs for many, many, many kilometres parallel to that conveyor. And you don't earth the line well, you don't have a good earth wire on it. There's no shielding provided by that system, and you can create really big volts on the conveyor. Up in the Bowen Basin many years ago, there was a conveyor next to a 66 kV line, and I believe a crow landed at the very end of the line on a bit of a wet day, and the crow died, and every e-stop along the entire conveyor just exploded. Now, no one got hurt, but you can see how powerful that interaction can be. The low frequency induction phenomenon between a folded phase conductor and something else can be pretty dramatic. Having a good earth wire connection on that feeder can help improve that. It doesn't make it go away, but it can help improve it. On the downside, or the plus side of separation, it was really hard for me to find reasons to separate from the NSP, to be honest. But, you know, they will say, well, you'll need to assess the transfer risk from our system impacting you. And I think really that's the crux of why they want to isolate in some cases, you know. Separation can assist with lightning risk. I suppose if the line receives lightning strikes and you do have a separation somewhere, well then perhaps if it's built well and designed well, you won't see those transient voltages on your earthing system or at the mine, which maybe that's an advantage. Can work both ways. The NSPs feel like they want to limit their liability, which I find is a bit of a conundrum because they'll agree to a 66 or a 132 kV connection and they'll sign all the paperwork and you'll bond up your phase conductors and energise things and off you go. But they'll go, oh, but we're not going to create a connected earthing system. We'll give you the electrons, but if they go into the ground, well, that's your problem, not ours. We don't want them back. They'll get them back eventually. They can't avoid that unless they start doing crazy things, unearthing their transformers or doing something silly. I really think you need to get ahead of them and talk to them about that, about the need that we really want to connect our earthing system to yours because it's going to have massive benefits to us. Your one at Wilpinjong, I mean, that's an essential energy circuit. You've got earth wires connecting into your site, haven't you? I designed that years ago, many, many years ago. You want some reports on that, I might be able to find them. Although I think my filing system's as bad as yours. But then again, you know, and it depends on when it was or when it happens. I'll go back to that in a minute. No, I'll go back now, sorry. That was that photo I was going to show you before. It's in the wrong spot. It depends on who you're talking to as well, because I know when I helped John at Metropolitan, when he upgraded his 33 kV system, that was all cable fed. There was no question that the earthing systems were not going to be bonded between the supplying zone sub at Helensburgh and his new equipment at Metro. The cable design needed to be earthed at both ends. That's how it worked. And Endeavour Energy knew that at the time. They had a smart guy in the earthing role and he said, absolutely, it's going to be connected. More recently, I believe it's at Appen, they're saying, no, we won't let you connect. And they don't have a good justification why. They just feel like it's written in our design standard somewhere that you've really, really, really got to prove to us. So it's just, I find that they're just not, they've got to be careful, these guys, these NSPs, when they make these statements, because we all know now under our work health and safety legislation, we're bound to eliminate hazards. And if we can't eliminate them, we've got to reduce the hazard to as low as reasonably practicable. And if they want to mandate and create these isolations, well, they're going to have higher risks. So they're basically saying, due to a policy, we're going to enforce upon you higher risk, which doesn't work with the work health and safety legislation. So I feel like it's going to bite them one day when one of these foreseeable incidences happens and they have to stand there and try and say, well, it was written in our guide that you can't bond. Well, that's not good enough. It's got to be engineered properly. Yeah, here's one of these fancy cable separations where you really try and separate your surface workings from the underground using a breakout box. Pretty nasty thing to have to do, but necessary in some cases. All right, in closing, I've probably bored you to death. Obviously, our primary controls are bonding and separating, trying to manage lightning risks, trying to manage all of our earthing risks and so on. Bonding to the network earthing provider, almost always. In 20 years, I've never, ever assessed a transfer risk from a supplying zone sub down through an earth wire cable screen, and it's been a problem. Never, ever. So when you sit down with them and you say, hey, we want a new 66 kV connection, almost straight away say, and we want to bond the earthing together, unless you can tell us it's not a good idea. It should be that way around, not the other. And on that note, I will bid you adieu. Stay safe.